Hello, everyone. I'm Ryan O'Grady. I'm a research scientist with a small research company called SOAR Technology, and we focus on artificial intelligence, and in particular, I focus on the intersection of artificial intelligence and cybersecurity. So, I'm just going to say this up front. I get nervous, and when I get nervous, I talk really fast. When I talk really fast, so if I start talking too fast, just shout, slow down, okay? Otherwise, we'll be done in 5 minutes. So this talk is, your training data is bad and you should feel bad. And hopefully ways to make you not feel quite so bad. So how did this come about? Well, I had a pretty simple question. Can I detect botnet command and control on Twitter using machine learning classifier? So I started digging into that and going, okay, well, there's all these tools out there. All I need is some labeled data, right? Well, that's easier said than done. The availability of data is low, labeled data is almost non-existent, and recent labeled data, forget it. You just give up and go home. So then I started thinking, well, I found this data set from 2011. That's good enough, right? And it got me wondering, trends change, how people use technology changes. Is that data actually meaningful anymore? So I asked myself the question, how does data age? And more formally, to what extent does the recency of training data affect the performance of machine learning classifiers trained on that data? In other words, can I use old data to draw meaningful conclusions about new content? So what I was really interested in was, is a given tweet or set of tweets or account really a bot? Well, as I said, I don't have good data for that. So I thought, okay, if I want to answer this question about the recency of data, what information do I have? So I decided that verified as a stand-in for trusted is a reasonable place to start. So I started looking at, can I determine if a tweet comes from a verified account? Now I know a lot of you are thinking that's not the same as a bot. I know, but we have to start somewhere. So in order to answer this question, I needed to collect data. Thankfully, that's already labeled data. Each tweet includes whether it's from a verified user or not, so that makes my life easier. So I just need to go out and collect around 1,500 tweets for each year. The verified program was initialized in 2010, so that's where I started, was 2010. Thanks to the kind people at Twitter and the limitations they placed on the API, that meant I had to gather 4 million tweets. And I can get more into that later if you're interested, but basically, you can only get the 4,000 most recent tweets. And for a verified account, that might be a year. It might be less. So for each year, I trained a classifier with data from that year, and then tested it against data from every other year. So in 2010, I trained a classifier on that data. I then tested it against determining if tweets are verified or not in 2010, 2011, 2012, and so on, up to 2018. That gave me the data that you see in the upper left there, which is kind of a square year-by-year grid. But that's not how I think about the data. How I want to actually think about the data is, what is the offset between the training year and the test year? So you can see I shifted all the data so that all of the +0, meaning 2010 training data and 2010 test data, 2011 training data, 2011 test data, all lines up. And all of the conclusions I'm going to discuss are based on that representation of the data. You don't need to be able to read that, don't worry. I'm just showing you how that process works. So how did I actually measure the performance of these classifiers? Well, the first thing you're going to find if you start looking in machine learning is accuracy. Accuracy is a garbage metric. I didn't use it for reasons I'll explain. It's especially bad for what are called imbalanced classes, which for verified, that's exactly what it is. 95% of accounts are unverified. So what does that mean? If I'm a lazy machine learning classifier and I just say, yeah, sure, it's unverified, I'm going to be right 95% of the time. But I didn't do anything. So we needed to find a better way to measure performance. That's why I settled on the Matthews correlation coefficient. It uses all the elements of a confusion matrix. I won't get into that, but the bottom line for us is that if a lazy machine learning classifier says, yeah, sure, it's unverified, the correlation coefficient is going to be 0, meaning no correlation. It has to actually make predictions about the least and most popular class, in this case unverified and verified, in order for it to actually have any measurable impact on the correlation coefficient. I put an asterisk here because it doesn't matter. There are some edge cases where you just say it's equal to 0 and you just move on. But by and large, if you're predicting 0 for all the classes, this is going to be 0 at the end of the day. Each classifier was trained using three sets of features. The first is tweet-only features. Those are features of the tweet itself. The content, although I didn't actually use semantic content, I do want to make that clear. When it was made, how quickly it was made from the previous tweet, and so on. The second set is user-only features. These are features associated with the user account and not the tweet itself. When was the account created? How many friends do they have? And so forth. And then, of course, all features is both the user features and the tweet-only feature sets combined. So now getting to the actual meat of what I found. The first finding is that classifiers perform best at a +0 year offset. This means that if you train with data from 2017 and test against data from 2017, that has the peak performance. As you start moving away from a 0 offset, either positive or negative, performance decreases. Now, I know you're not gasping in shock. That's not a terribly surprising conclusion, but it's an important conclusion and one we want to be able to prove. There are some more interesting things in there. The performance of different classifiers varies. So any of the ensemble classifiers tend to perform best. Those are things like random tree, gradient descent, anything that combines multiple classifiers into one and can have a bucket approach. SVC fared the worst. Its +0 offset performance was not bad, but it quickly approached 0 as you moved away from 0 offset. I should go. When you look at these numbers, the 0.98, 0.91, and so forth, that's the Matthews correlation coefficient, which can be interpreted as Pearson's R. That means that a value of 0 is no correlation, a value of -1 is perfect negative correlation, and a value of 1 is perfect positive correlation. So what you're really looking for is a value approaching -1 or 1. So here you can see side by side the performance of the classifiers, the mean performance of the classifiers for the tweet-only versus the user-only feature set. You can clearly see that performance is optimal at +0 offset, and it does drop as you go positive and negative. You can also see that the user-only feature set performed significantly better than the tweet-only feature set. Finding 2, feature importance changes over time. Again, not really shocking, but I just wanted to make it clear that if you're using the same feature set that you derived in 2010 as in 2018, your performance is going to degrade. Using the tweet-only features, performance didn't really degrade because it wasn't good to begin with, so it went from bad to bad. For the user-only features, though, we saw a significant drop from 0.62 to 0.39. The biggest change was in the user friend count. So in 2010, your user friend count was a strong indicator of whether you're a verified account or not. In 2018, that's no longer the case. What this research doesn't do is try and answer why these features changed in the way they did, but that would be good future research. And here you can see a plot of the user-only features on the top and the tweet-only features on the bottom. There's a bit of an odd drop in 2017 that I couldn't explain, but the trend does hold. The third finding, adding more features doesn't necessarily increase your performance. That's an old, I don't know how old it is given the field, but it's a machine learning axiom. More features is better. Bullshit. I'm saying right here that if you add more features, if you add the all features, you add the tweet only features into the user features, your performance is getting worse. I can't tell you how many of my colleagues I talked to trying to figure out what features to include, and like just throw it all in there. You know, it's fine. It won't hurt the performance. Well, yes, it will. So you can't just skip the feature selection and feature extraction step of creating a machine learning classifier. That's an important step, and if you skip that part, you're going to hurt your performance. I should point out that certain classifiers were less susceptible to this. Again, the ensemble classifiers tended to fare better when you started adding extraneous features in there. Others, like SVC, I don't mean to pick on SVC, but it totally trashed its performance. So here you can see, again, the user-only performance is on the left, and it performed pretty well, +0, and it dropped off. But even at 0.6 on the left or 0.5 to the right of the user-only features, that's still a pretty positive correlation for performance. But once we added in the all features, added in the tweet-only features to that set, it only dropped the performance across the board. So what's the bottom line here? What does it all mean? Again, I don't want to shock anyone, but training with contemporaneous data is going to get you the best performance for your classifiers. That means, unfortunately, if you decide you want to go out and create your own Twitter bot classifier, you're going to have to figure out some way to get relevant recent data. If you just go and find some data set off the shelf that's been sitting there for 5 years, maybe you'll get some good data, maybe some good results, or maybe it'll get no better than noise. There were some of these classifiers that, by 3 years out, either positive or negative, were performing no better than if I had trained it on noise. And the conclusion you might draw if you're not careful is that your classifier or that approach to classification is faulty, when in fact it's just bad data. Again, machine learning isn't magic. Garbage in, you get garbage out. You have to be careful with how you select your training data. You have to be careful with how you decide which features to include, because including extraneous features can hurt your performance. And don't skimp on the actual feature selection itself and feature extraction. I just want to spend a moment to talk about, what are some of the future directions that I can see this going, and it points to some of the limitations of the research itself. So what I've done here is said, can I use data to determine if a tweet is from a verified or unverified account, with the assumption that that has some correlation to determining if a tweet is from a botnet or a non-botnet account. That's an assumption that needs to be explored. Does the same approach hold true given good botnet data? And then the Twitter limitations that I talked about, is the performance that's being observed here in spite of those limitations, or is it some artifact of those limitations itself? So, for example, I could only use verified accounts that had tweets from 2010 up to 2018. That right there is a limitation and self-selection criteria where a lot of other accounts were left out, especially high volume accounts were left out because they put out 4,000 tweets in the last 2 years. I couldn't use it. So what you really need is access to the full data stream so you can do proper random selection of the accounts and get the full set of data for any given account rather than the limited set you can get for the free API. Unfortunately, I didn't have $100,000 lying around, so I had to make do. And then finally, what would be the effects of including the semantic content? I left aside the tweet content itself entirely. Usernames, I didn't consider those. How does that affect the performance of any of these classifiers if you start looking at what they're saying? What is the sentiment? Do sentiment analysis, semantic content analysis, any of those things to try and get a better sense of what is the actual content of the account rather than just the characteristics of the metadata. So if you want the full paper, it's available in the Sans reading room. or if you trust a shortened link, there's the Google link. I did this research as part of the SANS Master's Program. I'm excited to be part of that, so if you want to talk to me about that, I'm happy to talk to you more about that program too. So I didn't go too fast, but I still have plenty of time left, so I'd be happy to answer questions at this point. So, just to ask myself a question, one of the things I'm often asked is, why do you see this performance? Why is there this degradation in feature mutual importance? And I couldn't answer that as part of the research, but I have given some thought as to, what's going on here? Why are features becoming less meaningful over time? And I suspect it might have to do with the fact that as the Twitter base grows, as it becomes more diverse, individual features are no longer as meaningful. You have accounts from all over the world. You have accounts from all different ages. So I think that as their base is growing, it's essentially watering down the significance of any given feature and decreasing what you can derive from that information. Yeah.
Did your features for this include whether or not there was a link?
It did not. There was actually no content analysis whatsoever. So if you want to see the features, so the tweet-only features, they're more or less Boolean features. Some of them are numeric, like how long it's been since the account was created. I didn't do any kind of, was there a link, was it a retweet? Actually, is a retweet is one of the characteristics, but it didn't, for example, look at, okay, who were they retweeting? Was it another non-verified account versus verified?
Well, maybe that's another interesting side. You could do like graph analysis or something in context.
Yes, and actually, shortly after I finished this research, a couple of researchers, I forget out of where, announced they had discovered a roughly 400,000 botnet account called the Star Wars botnet, which, I would love to get my hands on their data, but data sharing is its own quagmire. And if you want to look at the features for users only. Yes, ma'am. Mm-hmm.
So those are evolving too.
Absolutely.
I don't know, when you refer to scanning features in that question from the user, you were referring to something specific in Twitter or just in general?
So, you can do semantic analysis to try and, reconstruct the actual content and say, you can determine the language. I actually toyed with that. You can determine, is it content from somewhere else? You can do sentiment analysis to try and determine is it a positive or negative tweet. There's some more advanced techniques I'm not all that familiar with to try and essentially determine if it makes sense. Is it and in Twitter that I realize that's a bit of a sucker's game. But I haven't explored any of the actual sentiment analysis approaches. I filtered for English tweets. Yep. I filtered based on the language field specified by the tweet itself. There is a field that can specify what language the tweet is in. A lot of them come through as unknown. I didn't use those. I used only EN tweets. Yeah. Yes. Right. Mm-hmm. It was trial and error. Actually, a lot of this was trial and error. And part of what I wanted to see here was how various classifiers perform. So as you can see here, I did use 7 different classifiers, or 6 or 7, just to compare their performance. So the answer to your question is I didn't decide. I just chose some based on what's popular and what seemed to make sense for the data. There was before any of the rigorous science started, there was a fair amount of just exploring the data, looking at, what are the mean, median, mode for various fields, what are the outliers, that kind of thing. And then I started homing in on what I actually wanted to extract as features and what classifiers I wanted to use. I can tell you there were several long afternoons spent waiting for a k-mean classifier to finish up because I was using 30 features and that was going to take it 200 years to finish, and I didn't realize that until too late. So, yes.
Did you do any analysis of whether the changes that happened year over year were different in the negative cases versus positive cases?
Did I determine if there was changes in the negative versus positive year after year?
I guess what I mean is, like, it seems like the data set on which you're testing is changing over time, which is validating the effectiveness of the model. Do you know if that's changing similarly in the positive cases, the verified accounts, or the negative cases, where the background noise is getting shittier and but the verified accounts is getting the same?
Oh, I think I see what you're saying. So, no, I didn't. And actually, I'm going to point out, another shortcoming in my research, which is user data is as of the time you retrieve the tweet. Okay, so when I go and get a tweet from 2010, the user data is from 2018 or whenever I capture it. If the user data has changed significantly in that time, of course that's going to be reflected in the up-to-date, whereas the tweet-only data is as of 2010. So if I get a tweet from an 8-year-old account, the tweet looks like it did back then, but their friend count, number of retweets, all that is going to reflect current time. And that's just simply a limitation of the data that's available that I without capturing data across time, like I started 8 years ago, I don't have a good way to counteract that. Any other questions? All right. Well, thank you very much for your time.